Welcome to 6th episode of organic nitrogen compound and the 3rd episode on amines. We have already discussed in the earlier 2 lectures on amines, the classification and nomenclature. We have discussed structure and stereochemistry related to amines, and we have also discussed the basicity of amines in detail. In the present lecture, we are going to discuss methods of preparation of amines. Amines can be prepared by the reduction of nitro compounds. They can also be prepared by reduction of alkyl cyanides or by ammonolysis of alkyl halides. They can be produced by reductive amination of aldehydes and ketones. They can be synthesized in laboratory by Gabriel thalliumide synthesis. They can be prepared by Hofmann bromamide reaction. Other reactions which are used, which are more or less similar to that of Hofmann bromamide reaction, are Lossen rearrangement, Curtius rearrangement and Schmidt rearrangement. Then amines can also be prepared by the ammonolysis of alcohols and by the reduction of oximes and amides. Now we will start with the reduction of nitro compounds. Both aliphatic and aromatic nitro compounds on reduction give primary amines. You can see here that this is aromatic nitro compound and this is aliphatic nitro compound. Both of them, when treated with metal in presence of hydrogen catalyst, they form primary amines. Nitro compounds can be reduced in 2 ways. One is by catalytic reduction, in which a solution of nitro compound in alcohol is shaken with finely divided nickel or platinum catalyst or platinum metal in hydrogen gas. This method is restricted to the molecules which do not contain any group which can be easily hydrogenated, such as carbon-carbon double bond. In this particular example, you can see that we have a nitro group which will be reduced to amino group, and we have a carbonyl group also. But since carbonyl group is not affected by this catalytic reduction or by the reduction in presence of nickel, this method can be used upon this orthonitro-acetanilide. Similarly, this is the ester group and this is also not affected by the hydrogen in presence of catalyst, and that is why reduction can be carried out on this nitro compound. The second method of reduction is via metal and acid. In this reaction, hydrochloric acid is added to a mixture of nitro compound and a metal which is usually granulated tin is used. In the acidic solution, amine is obtained as its salt and the free amine is then obtained by the addition of base. You can see here this is nitrotoluene, para-nitrotoluene. Upon treatment with tin and HCl, it forms the salt which upon treatment with base generates free amine. Now this free amine is steam distilled from the reaction mixture. We have another few examples also here. This is 1-nitropropane which is reduced to propanamine, and this is para-nitroaniline which upon reduction forms paraphenylene diamine. The crude amine is generally contaminated. Crude means the amine which is produced after reduction. This is generally contaminated with some unreduced nitro compound from which it can be separated by taking the advantage of basic properties of amine. You have already studied in your earlier lecture that amines are insoluble in water, but their salts are. So what we do is we simply add acid into it, they are converted into their salt, they become soluble in water and then can be separated from unreacted nitro compounds present in the reaction mixture. This reduction of nitro compound is by far the most useful method of preparation of amines, since it uses readily available starting material and yields most important kind of amines, the primary aromatic amine. These amines can be converted into aromatic diazonium salts, which are amongst the most versatile class of organic compound known. the sequence for the preparation of different classes of organic compound is via nitro compound. That is, first the aromatic hydrocarbons are nitrated, they form nitro compound. Nitro compound upon reduction form amines, and then to diazonium chloride they are converted to, and then diazonium salts are converted into various classes of aromatic compound, about which we will discuss in our forthcoming episodes. The next method for the preparation of amines is via reduction of alkyl or aryl cyanide. When alkyl or aryl cyanides are reduced with hydrogen or nickel or lithium aluminium hydride or sodium in ethanol, they give primary amines. When the reduction is carried out using sodium and ethanol, the reaction is known as Mendius reaction. Here you can see this is alkyl cyanide. Upon reduction it forms primary amine, and aryl cyanide also produces aromatic primary amine. Synthesis via reduction of nitrile has a special feature of increasing the length of carbon chain. A primary amine is produced having one more carbon than the alkyl halide from which it has been prepared via nitrile. You can see here, if we undergo reduction of cyanide, we get primary amine. Now, from where this cyanide is prepared? Cyanide can be prepared by the reaction of sodium cyanide on alkyl halide. So, if you look at this alkyl halide, this is benzyl halide. When it is treated upon with sodium cyanide, it forms beta phenyl ethanamine. That is, there is addition of one more carbon here. We started with benzyl chloride and now we have added one more carbon. So, this is the advantage of reduction via cyanide method. Here in this particular example, this is 1,4-dichlorobutane, 4 carbon alkane with chloro group at 1 and 4 position. So, 1,4-dichlorobutane when treated with sodium cyanide, it forms this corresponding cyano compound, and this cyano compound upon reduction forms a 6 carbon diamine, which is called hexamethylene diamine. This is a very important compound because it is used in the polymerization reactions. Another method for the preparation of amines is via ammonolysis of alkyl halides. Alkyl halides react with alcoholic ammonia to form amines. The reactivity of various halides in this reaction is in the order of this, that is, alkyl iodides undergo the reaction fastest, then alkyl bromide and then alkyl chloride. The reaction is generally carried out by heating alkyl halide with ammonia under pressure. Displacement of halogen by ammonia yields amine salt, from which the free amine can be liberated by treatment with hydroxide ion. You can see here, this is alkyl halide treated with ammonia to give alkyl ammonium halide, and this from this alkyl ammonium halide primary amine is separated by treatment with sodium hydroxide. The reaction is generally carried out by heating alkyl halide with ammonia under pressure. Ammonolysis of alkyl halide is a nucleophilic substitution reaction. The organic halide is attacked by nucleophilic ammonia molecule. The ammonia here is a nucleophile because it is electron rich and provides electron here, and here there is formation of this primary amine. This is an example of nucleophilic substitution reaction. As with other reactions of this kind, that is nucleophilic substitution reaction, elimination tend to compete with substitution. That is, ammonolysis thus gives high yield with primary halides where substitution predominates, and low yield with tertiary halides where elimination predominates. This we will discuss with the help of example. These are certain examples where we are using ammonolysis of alkyl halide. This is toluene. This upon treatment with chlorine forms benzyl chloride, and benzyl chloride upon ammonolysis forms benzyl amine. This is propanoic acid. Upon bromination it forms alpha bromopropanoic acid, and this upon ammonolysis forms an alpha amino acid. This is ethene. When treated with chlorine, this chlorine adds on to the double bond and there is formation of 1,2-dichloroethane, which upon ammonolysis forms a diamine, that is ethylene diamine is formed here. Now we will discuss some disadvantages of ammonolysis in the formation of more than one class of organic compound. We have already discussed that primary amine salts are formed during the ammonolysis of alkyl halide. These ammonium salts upon treatment with ammonia forms primary amine. Now this free primary amine, like ammonia from which it was made, is act as a nucleophile and it too can attack the alkyl halide to yield the salt of secondary amine. That is, here we are using the primary amine as the base or as the nucleophile and there is generation of secondary amine. Similarly, the secondary amine once formed can act as a nucleophile and react with alkyl halide to generate a tertiary amine. And finally, the tertiary amine can attack the alkyl halide to form the compound with formula R4N X, that is quaternary ammonium salt. So, this is the disadvantage, that if we want to prepare only one class of amine, we do not get completely one class of amine, but we get mixture of primary, secondary, tertiary and quaternary ammonium salts also by the ammonolysis of alkyl halide. But in presence of excess of ammonia, the yield of primary amine is more. Now, why is it that in excess of ammonia yield of primary amine is more? The reason is that during the reaction of ammonia and alkyl halide, primary amine is formed, which acts as a nucleophile. But if we compare the amount of ammonia with that of primary amine, the amount of ammonia will be more and that is why there will be competition between the two and more of primary amine will be formed. And that is why if we want to prepare primary amine in excess, then excess of ammonia is taken in the reaction mixture. We will now discuss another method for the preparation of amines via reductive amination of aldehydes and ketones. It involves the reduction in presence of ammonia. Primary amines may be prepared by passing a mixture of an aldehyde or a ketone and large excess of ammonia and hydrogen over nickel at 150 degrees centigrade, or by the use of sodium cyanohydridoborate. The reaction involves reduction of an intermediate compound, an amine, that is formed by the reaction of aldehyde and ketone with ammonia and that contains carbon nitrogen double bond. Here you can see this is an aldehyde, reacts with ammonia and form an amine called aldimine. This aldimine upon reduction, further reduction, produces a primary amine. Here it is a ketone, upon reaction with ammonia it forms an amine which is called ketimine and this upon reduction forms again a primary amine. But if you compare the two amines, primary amines, what is the difference between the two? In this particular case, the amino group is attached to a primary carbon, whereas here it is attached to a secondary carbon. So, this kind of amine preparation is possible only with reductive amination of aldehydes and ketones and not possible with ammonolysis of alkyl halide. Now, if a primary amine is used in place of ammonia, it produces a secondary amine, and if a secondary amine is used in place of primary or secondary ammonia or primary amine, then it will produce a tertiary amine. So, reductive amination has been used successfully with a wide variety of aldehydes and ketone, both aliphatic and aromatic. You can see here that aldehyde or ketone can react with ammonia, produce primary amine, can react with primary amine, produces secondary amine, and when reacts with secondary amine, it produces a tertiary amine. So, all the three classes of amines can be prepared in good yield by the reductive amination of aldehydes or ketones. We will again discuss a few more examples here. You can see that this is acetone reacting with ammonia and hydrogen in presence of nickel and produces corresponding amine, that is 2-aminopropane. This is a secondary butyraldehyde or isobutyraldehyde reacting with a primary amine. Therefore, it produces a secondary amine. And here you can see this is ethanol or acetaldehyde reacting with a secondary amine, that is dimethylamine, and produces a tertiary amine. Here are a few more examples. This is acetophenone, which upon reduction forms 1-phenyl ethanamine, and in this particular example cyclohexanone is treated with ammonia. It forms an amine which upon reduction forms cyclohexylamine. The advantage of reductive amination over ammonolysis is that the reductive amination of ketone yields amine containing secondary alkyl group in good yield. Such amines are difficult to obtain by ammonolysis because of the tendency for secondary alkyl halide to undergo elimination. For example, here you can see cyclohexanone is converted into cyclohexylamine, a primary amine, whereas via ammonolysis we are not able to produce the amine. See, here this is cyclohexanol. When it is treated with potassium dichromate, that is it is oxidized, it forms cyclohexanone, and which upon reaction with ammonia followed by reduction forms cyclohexylamine. If we undergo the reaction of cyclohexanol with phosphorus tribromide, there is formation of bromocyclohexane, and this bromocyclohexane when treated with ammonia does not form cyclohexylamine. On the contrary, it undergoes elimination. So, this is the advantage of reductive amination over ammonolysis. The disadvantage of reductive amination is that the yields are poor in the reaction due to side reaction, and during reductive amination the aldehyde or ketone can react not only with ammonia but also with primary and secondary amine that have already been formed, and thus produce certain amount of secondary amine and tertiary amine as byproducts. As you can see here, a primary amine reacting with aldehyde or ketone and giving secondary amine. We will now discuss Gabriel thalamide synthesis for the preparation of primary amine. This synthesis is a very good method to prepare primary amines in pure state. It is an indirect method of transformation of alkyl halide to primary amine without the formation of secondary or tertiary amine as byproduct, which we have already seen in case of ammonolysis of alkyl halides. The first step in Gabriel thalamide synthesis is the reaction of thalamide with potassium hydroxide to form potassium thalamide. In the second step, nucleophilic substitution on an alkyl halide takes place and there is formation of N-alkyl thalamide. In the third step, acidic hydrolysis takes place and primary amine is formed along with phthalic acid. You can see here this is thalamide. It has a nitrogen attached to hydrogen, and this hydrogen is quite acidic in nature because of the presence of these two electron withdrawing carbonyl group. Now, because of this, when we treat this thalamide with potassium hydroxide, the acidic hydrogen is replaced by potassium and we get potassium thalamide. This potassium thalamide undergoes nucleophilic substitution reaction on an alkyl halide and there is formation of N-alkyl thalamide. This N-alkyl thalamide upon hydrolysis with water produces this phthalic acid along with primary amine in very good yield and pure form. We will now discuss another method for the preparation of primary amines starting from acid amide. This reaction is called Hofmann's bromamide reaction. Acid amides on treatment with bromine in presence of alkali at about 340 Kelvin temperature undergo rearrangement to form amine with one carbon atom less than the starting amide. Please remember, in the beauty of this reaction is that if we want to reduce the number of carbon and prepare an amine, then Hofmann bromamide reaction is one of the very good methods. Here you can see that this is a amide, and when we undergo the reaction, this amine is formed and this carbon which is forming carbonyl group over here is lost during the reaction. So, amine is formed from amide and there is one carbon atom less than the starting amide. You can see here a few more examples. This is acetamide forming methanamine, 2 carbon amide forming 1 carbon amine. Here it is in this particular example, this is butanamide, 4 carbon amide producing 3 carbon amine, normal propanamine. And here in this case also, even though we have a carboxylic group here and in the cyclopentane we have 2 methyl substitution, the amide group here is converted into amine. So, this Hofmann bromamide method can be used for the preparation of a number of compound of different utilities. The Hofmann bromamide reaction is believed to proceed via 4 steps actually. In the first step, it involves the halogenation of amide. You can see here this is the amide and this OBr minus which is formed by the reaction of bromine and sodium hydroxide. This replaces or takes away one of the hydrogen from amine and there is formation of this N-bromoamide. In the second step, abstraction of proton attached to nitrogen in N-bromoamide is done by the hydroxide ion. Now, abstraction of this proton from N-bromoamide is facilitated because of the electron withdrawing nature of bromine. This abstraction of proton is facilitated by the presence of electron withdrawing bromine, which increases the acidity of this amide hydrogen. Then an unstable salt is formed and in some cases this has actually been isolated also. In the third step, it involves the separation of halide ion which leaves behind an electron deficient nitrogen. You can see here this bromide also goes off and this nitrogen has only 6 electrons and it is an electron deficient nitrogen. And in the step 4, the actual rearrangement occurs where the carbon having the alkyl group migrates with the pair of electron to electron deficient nitrogen. Now, these two steps, that is step 3 and 4, they actually take place simultaneously. We will discuss this in the forthcoming slides, that how these two steps actually are taking place simultaneously. So, we can also write third and fourth step together, that is migration of alkyl group and removal of bromide ion together like this. In the next step, the hydrolysis of alkyl isocyanate takes place to produce amine and carbonate ion. This is isocyanate which is produced by the migration of alkyl group, which upon reaction with alkali forms a primary amine and carbonate ion. It is important to mention here that the migrating group migrates from atom to atom, but it does not jump. And since Hofmann bromamide reaction involves 1-2 shift of alkyl group with its pair of electron to electron deficient nitrogen, its stereochemistry involves complete retention of configuration in the migrating group. It involves 1-2 shift, very similar to rearrangement of carbocations. In the rearrangement of carbocations, if you recollect, a group migrates with its electrons to an electron deficient carbon. Here the alkyl group migrates with its electrons to an electron deficient nitrogen. The strongest support for the mechanism is the fact that many of the intermediates formed during the rearrangement have been isolated and that these intermediates have been shown to yield products of the Hofmann degradation. This Hofmann rearrangement is an example of intramolecular rearrangement because the rearrangement proceeds with complete retention of configuration about the chiral center of the migrating group. For example, when optically active alpha phenyl propionamide undergoes this Hofmann degradation, alpha phenyl ethylamine of the same configuration and of essentially the same optical purity is obtained. You can see here in this particular example, the carbon attached to amide group is a chiral carbon. Now, the optical rotation of this particular compound is dextrorotatory, showing a positive sign, and when it undergoes Hofmann bromamide reaction, this amide group is converted into amino group. But during the reaction, there is no change in the configuration of the chiral carbon present in the amide, and that is why there is complete retention of configuration and compound or amine of optical purity is obtained during the reaction. Nitrogen actually takes the same relative position of the chiral carbon that was originally occupied by carbonyl carbon, and the chiral carbon forms a partial bond with nitrogen before breaking away from the carbonyl carbon. This can be seen in this figure, that here it is the amide and this is the chiral carbon. Now, if this carbon-carbon bond breaks without forming a bond between this carbon and nitrogen, then there is possibility of change of configuration. But what happens in the transition state is that this carbon-carbon bond does not break and this carbon-nitrogen bond actually starts forming, so that when this carbon-carbon bond breaks, the configuration of the adjacent chiral carbon does not change at all. So, the migrating group moves from the carbon to nitrogen via a transition state in which carbon is pentavalent. You can see this carbon is pentavalent. This is attached to 3 other groups along with this carbon and nitrogen. As mentioned earlier, step 3 and step 4 of the mechanism are believed to be simultaneous. That is, the loss of bromide ion and migration of alkyl takes place simultaneously. The chances of formation of highly unstable intermediate in which an electronegative element like nitrogen has only a sextet of electrons are very rare, and such a species is even less stable than the primary carbocation, and that is why the third and fourth step actually takes place simultaneously. Now, another point here in Hofmann bromamide reaction is that it has been found that when migrating group is an aryl group instead of alkyl group, the rate of degradation is increased by the presence of electron releasing substituents in the aromatic ring. This is an amide forming an amine, and this is the aromatic ring. If in the aromatic ring we have electron releasing substituents, then it has been found that the rate of this reaction is faster. Now, we will find why is it so. The presence of an electron releasing group stabilizes the transition state and speeds up the rearrangement. Electron withdrawing group like nitro or cyanide have reverse effect on the reaction rate. Now, you can see here that in the transition state there is development of positive charge, and this positive charge is subsides, or you can say stabilized by the presence of electron releasing group, whereas electron withdrawing group will have the reverse effect, and that is why electron releasing substituents on benzene ring facilitates Hofmann bromamide reaction. We will now discuss a few rearrangements where primary amines are formed via the same kind of mechanism, that is via the formation of alkyl isocyanate. One such rearrangement is Lossen rearrangement, where a hydroxamic acid derivative is converted into primary amine. This is hydroxamic acid derivative, and this forms primary amine upon a rearrangement. In Curtius rearrangement, we start with acyl azide, which rearranges to form isocyanate derivatives on heating. Acyl azide in turn can be prepared by the reaction of acyl chloride with sodium azide, or by the reaction of ester with excess hydrazine followed by reaction of acyl hydrazine with cold nitrous acid. Another similar kind of reaction which utilizes isocyanates, alkyl isocyanates, is Schmidt reaction, and it is a variation of Curtius rearrangement in which carboxylic acid is heated with hydrozoic acid in presence of acid catalyst, and then there is formation of isocyanate which rearranges or which upon hydrolysis forms primary amine. Then amides can also be prepared from alcohols, and this is the industrial method of preparation of alcohols. In this method, aliphatic amines of low molecular masses are prepared on a large scale by passing a mixture of alcohol and ammonia in vapor phase over heated alumina or thoria at about 300 to 400 degrees centigrade. This method forms a mixture of primary, secondary and tertiary amines, and if ammonia is used in excess, then primary amine is the major product. Another method for the preparation of amines is by the reduction of oximes. Primary amines can be prepared by the reduction of oximes with lithium aluminium hydride or with hydrogen and nickel. Here this is the oxime of a ketone and this is the oxime of an aldehyde. So, oxime of both aldehyde or ketone can form primary amines. The reduction of amide also forms amines. Amides on reduction form primary amine, whereas N-substituted amide upon reduction form secondary and tertiary amines. You can see here that this is a simple amide. Upon reduction with lithium aluminium hydride, it is forming primary amine. This is N-alkyl amide forming secondary amine, and this is N-dialkyl amide. This forms tertiary amine upon reduction with either lithium aluminium hydride or by reduction by using sodium and ethanol. So, in the today's lecture, we have discussed various methods of preparation of amines. We have prepared amines from the reduction of nitro compound, by the reduction of alkyl cyanides and by the ammonolysis of alkyl halides. Then we have also prepared amines via the reductive amination of aldehydes and ketones. Gabriel Thalamide synthesis utilizes or it is used for the preparation of primary amines in good yield and in pure form. Then Hofmann bromamide reaction is also another method for the preparation of amines, where the amines are prepared from amides and one carbon atom less than the starting amide is present in the amines. Then other methods of preparation of amines comprise of Lossen rearrangement, Curtius rearrangement and Schmidt rearrangement. And lastly, we discussed the preparation of amines via the ammonolysis of alcohols and by the reduction of oximes and amides. Well, in the next lecture, we will discuss reactions of amines like acylation or alkylation reaction. We will also discuss electrophilic substitution reaction on amines. Thank you very much.